welcome you all in this presentation related to the subject fundamentals of surface engineering. And we are talking about the surface modification using third type of the method, wherein a layer of the required material having the requisite set of the properties is applied onto the surface of the substrate, so that required or expected improvement in the properties of the surface can be enhanced for improved wear and tribological performance. So, in this connection means what are the basic fundamentals related with the various processes which are used for surface modification by developing a layer onto the surface of the substrate. In the previous presentation I have talked some of those fundamentals, and in this presentation I will be talking about those fundamental aspects related to the surface modification, where in the welding is used as a process for surface modification of the substrate. So, in case of the welding, basically a layer of the required material, this is selected as per the requirement or the set of the properties which are desired at the surface. So, a layer of the required material is applied on the surface of substrate in this approach, which is called weld surfacing, when metal is deposited using a welding process. So, this is the surface of the substrate. So, we have to melt the substrate material up to certain depth while depositing the selected material onto the surface like this. So, this kind of the layer is called bead-on-plate weld. Bead-on-plate weld. It is, in short, it is termed as BOP weld. So, bead-on-plate weld is deposited to have a layer of the required material onto the surface of the substrate. So, properties of the surface can be enhanced. However, the performance of such a layer being deposited is influenced by performance, means mechanical and tribological performance of such kind of the layer which is being applied onto the surface of the substrate is influenced by the various factors, like how effectively we are able to protect the metal while it is being applied or while bead-on-plate is being bead-on-plate weld is being developed. So, the protection of the weld metal when the bead-on-plate weld is being applied. The second aspect is what is the cooling rate which it experiences during the solidification. So, cooling rate experienced by the bead-on-plate weld during the solidification or after solidification, both have effect on the properties of the layer which is being applied by the weld surfacing. Then we have the dilution, the kind of change in chemistry of the metal being applied onto the surface of substrate by fusing both in case of the weld surfacing. So, what is the extent of change in composition that is expressed in terms of the dilution. So, greater is the dilution, greater will be the change in composition of the layer of the metal which is being applied. So, there will be greater possibility for increased degradation in quality. So, it is always desired that dilution is as less as possible, and like dilution and the cooling rate both to a great extent are influenced by the energy density associated with the that welding process which is being used. So, in general, how much energy is being applied over a unit area. So, that we express in terms of the watt per mm square or watt per centimeter square. Mm square is more commonly used unit. So, over a small area we are applying the large amount of the energy, or over a large area we are applying the given same amount of the energy. So, that will bring in the change in the energy density, and this will in turn affect the heat which is required for melting. And if the heat required for melting is increases in case of the low energy density, then it will be reducing the cooling rate, it will be increasing the dilution. So, it is important that what is the energy density associated with the particular welding process which is being used. Lower is the energy density, increased heat input, lower cooling rate, increased dilution, and these kind of factors will tend to compromise with the quality or the performance of the weld surfacing which is being applied. Now, we will look into these aspects little bit in greater detail. So, we have the aspects like protection, the cooling rate, dilution, and energy density associated with the process. So, we know that when the metal is brought, you see what we do in the weld surfacing, either the electrode or the filler metal which is being applied, which is that should be melted, and a thin layer of the substrate should also be melted, and intermixing of both molten metal will be leading to the formation of the bead on plate or weld surfacing. So, you know, since the things are brought in the molten state and at a high temperature, it will have tendency to interact with the atmospheric gases. So, when the molten metal interact with the atmospheric gases, it can either dissolve the gases, or it can form some kind of the compounds like oxides, nitrides. So, dissolution of the gases and their limited escaping tendency will be leading to the formation of the pores or the blowholes. While in case of the formation of the compounds due to interaction of the molten metal with the atmospheric gases, it will be leading to the formation of the inclusions. So, it is not good that molten metal is interacting with the atmospheric gases which are present all around, and therefore, we need proper protection, and for this purpose in different welding processes different protection approaches are used. Like protection of the molten metal is needed to reduce the formation of the inclusions, pores, and other discontinuities which are being formed due to the interaction of the molten metal with the atmospheric gases, and therefore protection is needed. So, protection in case of like say the gas welding, it is very poor because we primarily use the fluxes which will be interacting with the impurities and will be helping to clean it. So, basically the fluxes are used to remove the impurities and the compounds which are being formed. In general, it is poor, and this happens primarily due to the higher oxygen and nitrogen concentration in the weld which is being produced. While in case of the shielded metal arc welding process, it is the thermal decomposition of the flux coating leads to the formation of the inactive gases, gas cover all around the pool. So, like there is an electrode having the coating all around the core wire of the electrode, an arc is established between the substrate and the electrode, and due to the heat of the arc, these flux coatings will be thermally decomposed and will be producing the inactive gases all around it in form of CO, CO2, and these inactive gases will be forming a blanket or cover all around the molten pool, which will be protecting the molten metal from the atmospheric gases. So, inactive gas cover is formed. This is somewhat better than what we get in case of the gas welding, but still oxygen content is higher in case of the shielded metal arc weld beads which are deposited using this process. While in case of the gas metal arc welding or gas tungsten arc welding processes, we use inert gas cover to protect the molten metal pool from interactions with the atmospheric gases, and for this purpose we may use argon or helium or mixture of the argon plus carbon dioxide, or even CO2 is also used in case of the steel. If the ferrous metals are to be processed by ferrous metals are to be deposited, then even CO2 can also work to provide the required protection. Then for plasma also invariably the inert gas mixture is used. For electron beam welding weld deposition using the electron beam process, we use basically vacuum to take care of all atmospheric gases so that they do not interact with the molten metal, while in case of the laser beam it can be performed under the influence of the inert or inactive gases, inert gases like argon or helium, inactive gases like CO2. So, these are the different approaches associated with the different processes. Since the approach of the protection of the molten metal from the atmospheric gases is different in each of the processes, and that is why the quality of the bead-on plate which is deposited with regard to the oxygen and nitrogen content which is there in the bead-on-plate weld, that will be different, because we are using the different approaches for protecting the molten metal from the atmospheric gases, and therefore the presence of impurities also differ. So, especially the cleanest weld will be produced by the vacuum based processes, then maybe GTAW process also results in very low level of oxygen and nitrogen content, and if we have very few impurities and these gases, then chances for inclusions, porosity, etc. will be reducing, and that in turn will be helping to increase the performance of the bead-on plate surfacing. Now, the cooling rate is the another aspect. In case of the cooling rate, like cooling rate affects the solidification time. Like we have got one bead-on plate pool of the molten metal which is to solidify. So, that solidification time will depend upon the cooling rate, how fast heat is being extracted from the molten zone. So, if our heat input is less, then the surrounding metal will be cool and heat will be extracted at a faster rate. So, this will be leading to the increased cooling rate, and increased cooling rate means the solidification time is reduced, and reduced solidification time or increased cooling rate means less time is available for growth of micro constituents which are there, and less means the availability of less time for growth of micro constituents means the temperature will be reducing from the molten melting point to the room temperature at a much faster rate, and therefore the time available for growth of micro constituents is reduced, and that in turn will be reducing the grain size. So, it will be leading to the fine grains, and we know that as the grain size is reduced, there is improvement in mechanical properties in general, hardness, toughness, ductility, fracture resistance all improve. So, improvement in mechanical properties, and this improvement in mechanical properties will also be leading to the improvement in tribological properties. So, it is important to see that how the change in welding processes, change in the conditions which are being used for depositing the bead on plate will be affecting to the cooling rate, and which in turn will affect the kind of the solidification time which will be experienced by the molten metal during the bead on plate deposition, and that in turn will be affecting the microstructure as well as the mechanical properties. Apart from the grain size, sometimes if the material is having the tendency to get tendency for the hardenability, then it will be leading to the change of the phases also, like under the low temperature, low cooling rate conditions, we may get the perlite, benite kind of the phases, but if the cooling rate is high, then we may find the martensitic transformation. So, not just the grain size is affected because of the cooling rate, but we may also find that the different types of the phases are being formed, and the difference in phases will further lead to the change in mechanical properties. Now, other two aspects are like dilution and the energy density. Now, we know that this the process of the weld surfacing for surface modification is based on the approach of applying a layer of the good quality material over the surface, so that required improvement in properties can be achieved. So, the material which is being applied is really of the good quality, but when it is applied using the weld surfacing, part of the substrate will also be melted. So, the composition of the material being applied is modified. The extent of change in compositional modification of the material which is being applied after the deposition of the bead on plate will depend up to what extent or up to what depth base metal has been melted, and that in turn will be determining the extent up to which change in composition of the material being applied is taking place. So, this in turn directly affects the mechanical properties and the quality of the surface layer which is being developed. For example, like say when we have the mild steel as a substrate and we are applying the austenitic stainless steel. So, mild steel costs like 50 rupees kg and austenitic steel may be costing like 250 rupees kg. So, there is a five-fold change in the price. The good quality material will obviously be offering the better combination of the properties, and at the same time it will be costlier one. But when one layer is applied like this, we find that austenitic stainless steel which was having like 18 chromium, 8 nickel and very limited carbon content like 0.05%. So, this is expected to be of the good quality material when it is being applied like AISI 304 kind of the material when it is being applied, but when it mixes with the mild steel after the melting, there may be reduction in the chromium content which may be reduced as per the extent of the substrate melting. Chromium content may come down to the 12%, nickel may come down to the 4% or 5%, and the carbon content may increase because mild steel will be having the higher carbon content, like it may reach to the 0.1. So, there can be significant change in the composition of the layer which is being applied. So, this is the story of say for the first layer. If we apply the second layer, then of course, the extent of dilution or the kind of change in composition of the bead on plate material which is being applied, that will be less. So, the extent of dilution will keep on reducing as the number of layers being applied. So, if we see here, like when one layer is applied, say dilution level may be 20%. When the second layer is applied, dilution may come down to just like say 10%. Then third layer may further be leading to the reduction in the dilution, which means the extent of change in composition of the surface layer material which is being applied in form of the bead on plate, that will be reducing. So, a degradation in composition or compositional modification due to the dilution, that will be reducing as we keep on increasing the number of layers. But the first layer, of course, which directly mixes with the molten metal, its composition is most severely affected, and the maximum change in composition is experienced in that case. Energy density is is another important factor. Energy density of the different welding processes is different. Like if here we have the welding processes in the x axis, just to understand, and energy density in watt per mm square in the y axis. So, the gas welding offers the lowest energy density, because the flame is very wide and the energy whatever is being transferred, that spreads over a larger area. So, energy density is less. While in case of the arc is of smaller in diameter, like 5-6 mm diameter of the arc at the bottom. So, energy density is high for a given set of the parameters if we compare with the gas welding. So, it offers the higher energy density for shielded metal arc welding process. Gas welding and gas tungsten arc welding process will be offering the further higher energy density, and the plasma will be offering the further higher energy density than we have the laser and electron beam. So, there is a continuous change in the energy densities associated with the different processes. Now, we will understand, like if H is the amount of heat required under ideal conditions, then using the process which is offering the low energy density, we need to supply the heat for longer time using the low energy density process, so that required amount of the heat can be supplied. So, this is simple time, we need to supply for longer time. When the energy density is high, then it is required to supply the energy for a shorter period for same amount of the heat. But we know that when energy is transferred for a longer period, lot of heat or energy will be dissipated to the underlying low temperature base metal, and that is why actual amount of heat required for melting using the low energy density process that is higher as compared to the high energy density process, because the amount of heat which is transferred to the underlying base metal, that is significantly lower in case of the high energy density process. So, that is why what we in general say, that if the process of the high energy density, then it will be requiring the less heat input for achieving the fusion, for developing the weld surfacing. So, if we see on the and the reverse is true for like low energy density process will require higher heat input. So, like the gas welding will be requiring the higher heat input as compared to the like plasma arc welding, and if the for gas welding heat input is high, it will be offering the very large cross sectional area of the bead on plate, it will be offering the lower cooling rate, and it will be leading to the coarser grain structure, and this will be degrading the quality of the weld surfacing which is being produced. On the other hand, higher energy density associated with the plasma arc welding, it will be leading to the reduced heat input required for fusion, reduce the cross section of the bead on plate which will be produced, it will be leading to the higher cooling rate and finer grain size. So, this is like coarse grain size, and here we will be getting the fine grain size, and fine grain size in general results in the much better quality with regard to the mechanical properties and tribological properties. Further, there is one more aspect which can be added, is the lower energy density, higher heat input, greater will be the dilution level, while for higher energy density processes like plasma, the dilution level is reduced. So, this is the difference associated with the different energy densities associated with the various processes. So, this is the kind of relationship which between the various aspects associated with the welding processes, which will be affecting the mechanical properties of the weld bead-on-plate surfacings deposited by the various welding processes. There is another aspect associated with the advancement of some of the processes like simple gas tungsten arc welding or gas metal arc welding. Conventionally, both these can work both on AC as well as DC, but if we are using DC, it allows the control over the heat input or heat generated by the arc. When we use the AC, the heat generation on the at both the ends is equal, while in case of the DC, we can select the polarity suitably, like electrode can be made negative using the electrode negative polarity, or workpiece can be made positive, or reverse is also possible. We know that more amount of the heat is generated when workpiece is made positive. So whatever end is the whatever end is connected to the positive or negative terminal, we will see that electrode negative, wherever it is, that will be generating, that will at that end will be having the less heat generation, while wherever and with the electrode positive, the more amount of the heat is generated. But in case of AC, since the polarity keeps on changing on every half cycle, so the amount of heat being generated at both the ends will be equal. Say for example, if you want more heat generation, then this electrode will be made positive and workpiece will be made negative. This is workpiece, so it will be made electrode negative. And if we want that more heat is generated in the workpiece side, so workpiece will be connected to the positive terminal, so we will be making electrode positive polarity, workpiece will be connected to the positive terminal, and the electrode will be connected to the negative terminal. So, En and Ep, electrode negative, or this is the like reverse, this is the state polarity, and in otherwise it is reverse polarity. So, reverse polarity when the electrode is positive and workpiece is negative, state polarity is when the electrode is negative and the workpiece is positive. So, in this case we will be having the about 33% of heat generation in the electrode side and 66% of the heat generation in the workpiece side, or in the reverse is true for the electrode reverse polarity, 66% of the heat generation in the electrode side and about 33% of the heat generation in the workpiece side. So, amount of heat generated will be affecting the dilution as well as the cooling rate, and that is why we select the polarity suitably. Now, another aspect related with this is the pulsation. Like in normal case, the current magnitude remains constant. In the simple DC current, as a function of time, the current magnitude remains constant. So, we may choose like 150 ampere current for depositing the bead on plate. But if we use the pulsation and in case of the pulsing of the current between the background level and higher level and low level, like this. So, background level is maintained at about 25 to 30% of the peak current level, and its magnitude should be such that arc is remain stable. So, this may be like 50 to 60 ampere, and we may use like 200 ampere current for peak current. So, this is peak current and this is background current. For same value of the average current, we find that the heat generation, the heat input required in case of the pulsing for the similar kind of the bead on plate is less. So, basically the pulse variant of the GMAW or GTAW for depositing the bead on plate requires less heat, as compared to the conventional welding where constant current magnitude is used. So, if we use like the voltage of 15 ampere and same average current value of 150, then we find that the heat input is more in case of the conventional gas metal arc welding or gas tungsten arc welding, while in case of the pulse GMAW and pulse GTAW, heat input is less, and that is why with the pulse variant of the GMA and GTAW, the dilution is less, the cooling rate is high, and the structure is in general fine, and the mechanical and tribological properties are in general better. So, this in turn help us in getting the much better quality of the weld surfacing. Now, I will summarize this presentation. In this presentation, basically I have talked about the few fundamentals associated with the weld surfacing which affect the quality or the performance of the weld surfacing, and these are basically the kind of protection that we provide to the weld pool during the bead on plate deposition, the kind of cooling rate which is experienced by it, and the kind of dilution which takes place during the weld surfacing. Thank you for your attention.